right, so I'm gonna wrap up with a very whirlwind summary of analysis of variance and of multiple testing. The most likely reason that I think you'll want to do analysis of variance is in order to make inference on a categorical variable as a whole, not just per dummy variables. So in the coefficients in the regression tables that we saw before, there was, for the spider legs, there was a coefficient for each one of the different sets of spider legs, but nothing for spider legs as a whole, whether it makes a difference which set of legs it is. And this is where analysis of variance can come in. And importantly, doing an analysis of variance on this model is a different analysis of the same model. So we're going to take the exact same model that we fit before, the two-way analysis of variance with the leg type and the leg pair in it, and just perform a different analysis on it. Instead of just looking at summary fit, which gave the regression coefficients, we're going to do ANOVA fit, which will provide the analysis of variance table for that same model. So what we saw before were these estimates for each of the coefficients, along with a standard error and a p-value for each of those coefficients. What we see in the ANOVA table is somewhat different, and it's quite a bit simpler. There's no intercept, there's no dummy variables in it. You just see type, not type push. You just see leg, not leg L2, leg L3, leg L4. So there's just one row per variable in the model. And we have different information. There's no coefficients given for it. There's no estimates here, nothing to say, how much the mean differs between pushing and pulling or between different pairs of legs. We just see this degrees of freedom of 1 for type and 3 for leg, corresponding to the number of coefficients that we fit for each of those. And then 2 new columns, sum square and mean square. And these have to do with the variance that we're analyzing. The sum of squares is, so let's start from the bottom and go up. The sum of squares of residuals is just what it sounds like. If you take your residuals from the model, square them, and add them, you'll get 12.03. And then the mean square for that is just taking the sum of squares and dividing by the number of degrees of freedom. So 12.03 divided by 277 will give you 0.04. The sum of squares for each of these, the interpretation is a little bit different. The way you interpret this, or the way you calculate, one way you can calculate this sum of squares would be, you start with an intercept-only model, calculate the sum of squares of your residuals. You'll get some large value. That's like a trivial model, or a null model, we call it. Then you add type to the model, fit that model, and calculate your sum of squares of the residuals. And the difference between that intercept-only model and the model with just type in it, that difference in the sum of squares of residuals is 42.78. So this gives you a measure of how much adding type to the variable reduced your sum of squares of the residuals. And then again, mean square is just divided by the number of degrees of freedom, which is 1, so it's the same here. So this tells you in terms of sum of squares and mean squares, which is what really matters, there was a very big reduction in the variance of residuals from adding leg type to the model, whether it was push or pull. And then a quite a bit smaller reduction achieved by adding leg to the model, which kind of corresponds to what we saw in that box plot, right? The F value is actually very simple to calculate once you've gotten this far. All it is this mean square divided by the mean squares of the residuals. So if you have a reduction in variance of residuals from adding type that is much larger than what is left over, you're going to get a large F statistic like we have here. If you have a fairly small reduction in mean squares of residuals from adding a variable, your F value will be somewhat smaller. And it's just a ratio of this reduction in variance from adding the variable to the variance of the residuals, which people also describe as being, it's the variability between groups compared to the variability within groups. So if you have groups where there's a big difference between them and not a lot of variation within them, you'll get a large F statistic. So you can see it doesn't matter whether the difference in the groups is positive or negative, or if you have 2 groups or 5 groups. All that matters is, does adding that variable reduce your residual variance by a large amount compared to what's left? And that's why this table is so much simpler than the regression table, because we don't care about the individual, which leg pair. We only care about the fact of adding legs to the model at all and how much that helped reduce the residual variance. So if the assumptions of the F-test are met, that is normality, homoscedasticity, and independence of the observations, then that ratio will be distributed according to an F distribution. And this distribution, here is just one example. It has not just 1 degrees of freedom. You remember the T distribution, normal, there's just the mean and the standard deviation. For the T distribution, there was a degrees of freedom added to it. For the F distribution, there are 2 different degrees of freedom. There are the numerator degrees of freedom and the denominator degrees of freedom. So in this case, for type, the numerator degrees of freedom would be 1, and the denominator degrees of freedom would be 277. So both of those degrees of freedom matter. But always the distribution looks something like this, with a peak somewhere down near 1 and a long tail to the right. And doing inference on this, the idea is the same as it was using the normal distribution and the T distribution, in that we just want to calculate under this null hypothesis of the F distribution, what is the probability of getting an F statistic as extreme or more extreme as what we observe, with an important difference being that we only look in the right tail for the F distribution. And that is because any differences between the groups that helps you to explain variance will cause an increase in the F statistic. So what would an F statistic of something close to 0 mean? So it's the variability between groups divided by the variability within groups. What would an F statistic somewhere down here mean?
The variability within groups is larger than the variability between.
Mm-hmm. Yeah, so what it would mean is that your variability between groups is actually less than you would expect based on individual variability. So, you know, you imagine that in the case of the legs, there's a certain amount of, between say L1 and L2, there's a certain amount of variability for legs for L1 friction coefficients and variability among L2 coefficients. So just based on that individual variability alone, even if there's no difference between L1 and L2, you would expect some difference between the groups just because of differences between individual spiders. One way that you could end up with a very small F statistic would be due to poorly fabricated data. And there have been instances of research misconduct uncovered by an F statistic that is much smaller than you would expect for unrelated groups. They had a hypothesis that there was no difference between these groups, and they actually simulated data that way with no difference between them. So you create your several groups with absolutely no difference between them. You get a minuscule F statistic. That's just kind of an interesting note. And as to why it's really only a one-tailed test when we do inference from the F distribution. That's all I'm going to cover for analysis of variance. The most important thing that I'd like you to take is being able to read an analysis of variance table. To know what these mean squared values are, to know what the F value is, to know that, you know, the sum of squares is just the amount of that the variance of the residuals is reduced by adding this variable. The mean squares is the sum of squares divided by the degrees of freedom. The F value is this mean squares divided by the residual mean squares. And this probability of greater than F is based on the F distribution with here 1 and 277 degrees of freedom. One other, maybe that I'll just mention, useful application of analysis of variance is for comparing two nested models. You can fit, as long as you use the same data, you can fit models using two different model formula. They can be very different models, and you can, so this type analysis of variance and F-test is based on comparing a model with type and intercept to a model with just intercept. So it's comparing like a null model, intercept only, to a model with this one variable in it. But you can actually use ANOVA to compare any two models on the same data. And this ANOVA can actually take two fits as an argument, fit 1 and fit 2, where you use different model formula for them. And it will give you an analysis of variance comparing those two models rather than the default of intercept only to intercept with a variable added. So you can use it for comparing adding two variables at the same time to a model, or to adding the interaction terms to the model. So any it's a flexible way to compare different competing models and to say whether the reduction of residual variance offered by the more complex model is more than you expect just from the additional fitting and degrees of freedom used. Any questions about ANOVA?
And how many different formulas there are? It is ANOVA function and ANOVA.
The ANOVA and AOV both do analysis of variance. It's sort of like PrinComp and what is the other one? PC. Yeah, they give somewhat different output. They're doing the same thing. So you can try them. And I kind of like, I mean, ANOVA uses the same fitted object. AOV takes a model formula. So you would specify the model formula here. I kind of like this way just because I probably want to see the coefficients as well as the analysis of variance. So this is, you know, using that same fitted object for both. But you can try AOV and see.
But the length is only, you will use it with continuous. The length function.
Yes, you'll use LM only with a continuous response variable anyways. Another advantage to using this approach, ANOVA fit, is that fit can also be a generalized linear model. And so if you have a binary response variable for logistic regression, you can still do an ANOVA on that model. So maybe you could say ANOVA is more general. If you have some fitted model and it's possible to do an analysis of variance, then ANOVA will do it. So I'm not getting too much into inference in high dimensions because for the most part, it's just inference, as we've learned, repeated over and over. And typically Y would be gene expression or some other continuous measure. Microbial abundance, something that is a numeric measure, and X would be your your groups, your experimental factors, etc. And that's all there is to it, with a note that for small sample sizes, some Bayesian improvements can be made. And this is what the lemma package does, DESeq2 does it, but it really only makes a difference for small samples. For larger samples, you can just do it one at a time. And it's in prediction and machine learning where we have the many predictors. Like if you're trying to predict outcome based on gene expression, then it's something different. And this is where machine learning, support vector machines, regularized regression, all these more exotic things come in. But for the purpose of inference, differential expression, differential abundance, there's nothing exotic about going to high dimensions. It's just repeating the same thing over and over and doing multiple testing correction. And the reason we have to do multiple testing corrections is that anytime you're testing more than one hypothesis, even if all of those null hypotheses are true, if you set your alpha to 0.05, you expect a 5% type 1 error rate, which means that, and if all of your null hypotheses are true, then all of your p-values less than 0.05 are actually false positives. But with multiple testing, you can estimate which of those p-values are actually smaller than you would have expected by chance if all of the null hypotheses were true. The two mainstream approaches are family-wise error rate correction, particularly the Bonferroni correction, This one's very simple. You just take your p-values and multiply them by the number of tests you've done. And if you control your family-wise error rate at 0.05, it ensures that your probability of having any type 1 error, so even just one, remains at less than 0.05. So it means that you can be fairly confident that all of your rejected null hypotheses are in fact false nulls or alternative hypotheses. The other even more common approach is the false discovery rate, with the main test being the Benjamini-Hochberg correction. And it's somewhat different in that it doesn't try to say you will have no false discoveries among your rejected nulls. It'll just control it so that you have a certain rate of false discoveries among those. So you would then, if you set your FDR to 0.05, it means that you expect that 5% of your rejected nulls are type 1 errors. This is an interesting note to keep in mind, that for your smallest p-value, the FDR correction by the Benjamini-Hochberg method is the same as the Bonferroni correction. And then it's for your subsequently larger p-values that correction becomes less stringent. These methods and others are available in base R using the p.adjust function. You just provide a vector of your unadjusted p-values, say what method you want to adjust it by, or if you don't specify it, you'll get all of the different methods adjusted. Very simple to do these adjustments. It doesn't affect your tests at all. You just take your p-values, hand them over to p.adjust, and get your adjusted p-values. P is the original unadjusted p-value. I think p.adjust gives you a matrix with your original p-values and your adjusted p-values. But yes, p is just a vector. Yeah. If you use a package for high-dimensional inference, such as Lemma, EdgeR, DEC2, they will, as part of the calculations, provide you with adjusted p-values. But there's nothing wrong also if you have a large sample size. You can just do your regression row by row and then apply an adjustment.
Can you present it like also this is a result together with the result of the ANOVA?
Well, so the results would usually be something like a list of differentially expressed genes, perhaps a heat map showing your differentially expressed genes, maybe a box plot showing the fold change for your differentially expressed genes, a list of the number of them, a gene set enrichment or pathway analysis of those genes. And that brings us to the summary. So just to summarize, linear models, they're what we use to identify differential expression or differential abundance, even in cases where we don't have normally distributed residuals, where we have a binary response variable or count data. There are extensions to linear models called the generalized linear model framework that we can still use. But for ordinary linear models, keep in mind these assumptions, and also just keep in mind the extension. These extensions are actually not that difficult, which is why I tried to focus on the model formula and the model matrix and understanding some of these outputs, because going from LM to GLM for a generalized linear model, it's not too much of a stretch, and the model formula framework is the same. Your reading of the outputs is similar. It's not quite exactly the same, but you're much of the way there anyways. And you can use the model formula interface most of the time, but remember that there are model matrices available to you if you want to fit coefficients that aren't produced by your model formula. All right, and for the lab time, I thought we would just continue from last week, or you can in fact just, I want you to be making progress on your projects, and just you can work on questions 1 and continuing on in the beginning of the project. If you're interested, I can do these couple of analyses up on the screen if you would like me to. Otherwise, if you'd rather just work on your project or do this, I can, since there are only 2 of you, it's easy for me to take a look and help out with your own data set.
I started with the boxes, but I cannot use this math SE. I cannot extract from the sample info the date from my dataset.